Welcome. My name is Gurvin. I'm a project manager at the Norwegian Cognitive Center, and I welcome you at the scene here and also online. We are here to prepare organization for the change who is coming the next year, because AI will be the most important single factor that contributes to value creation for a large number of industries. And what we see that the Statistics Sentralbyrå see is that Norway is way behind using AI in Norway. Other using it or planning to use it. And this is a challenge for us. On Tuesday at Vestlandskonferansen, Norwegian Cognitive Center and Bergen Næringsråd will relieve a survey that we have taken from the companies from west of Norway, from Stavanger to Ålesund. And this is really an eye-opener. We need to act, and we need to act now. And this is also why we have established Norwegian Cognitive Center as a project. The project is owned by 5 different industry clusters. It's media, it's finance, it's ocean, it's seafood, and it's PropTech. And we, together with partners like IBM, Norse as a researcher, universities, and also private and public companies, is behind this project. And we are a non-profit project. Financed by those industry clusters, among Innovation Norway, Bergen Kommune, and the greatest contributor is Agenda Vestland, to try to increase the use of cognitive technologies, meaning putting AI, machine learning on top of your data, so that we compete in a much better way in the years to come. And what we also offer is a sandbox where you can come in with your own data, you can add public data or other kinds of data, and you can build, test, and run application in this sandbox. And we don't care where you have your data or where you're transporting them further on. We also help you, organization, to identify use case. We also supply you with approximately 10 hours of either a data engineer or a data scientist who can help you start your journey within using AI. And within this sandbox, there are nearly 400 different tools that you can use, and it's free to use, and it's secure. The governance is taken care of, and it's up to you. If you have the use case, you want to test, and you want to try it out, just reach out to us. Also, we have worked with and met nearly 200 companies the last couple of years. And we see that we have to go a bit back to the start. And we are now launching what we call ABC course within AI. So the first cluster out is GCA Ocean on the 21st of April. There is a 6 hours course together with Digital Norway. And that's aimed for people who works in the business, not technologies, but business developers, manager, middle management, etc. Because we need to raise awareness of how to use cognitive technologies on top of the data the organization already have. And the course will also be available for Innovation, NCA Finance, NCA Seafood, and NCA Media after this first course. now we're going to hear 3 different cases from different kinds of players who has worked with AI, and those guys will introduce us the tools and techniques they are using in their solution.
So thanks for having me. My name is Erling Risa and I work at Sparebanken Vest. And today I'll be talking about how we use data science to combat money laundering. So first, quick introduction. I joined Sparebanken Vest in 2019 following a PhD in economics, and I've been working on a range of topics since then, but the ones relevant to this presentation is modeling credit risk and money laundering type problems. So quickly about the presentation. So when putting together the presentation, I decided to focus on reasoning and intuition and sort of the challenges that we've faced when trying to tackle this problem, rather than getting super into the nitty-gritty technical details of this specific problem. And I'll be talking about 2 different approaches to anti-money laundering, where the first one is as a form of anomaly detection, which takes us to the world of unsupervised learning. And the other one is a more standard prediction approach, where we're in the world of supervised learning. And also, so why is money laundering sort of an interesting statistical problem? And I mean, the starting point for that is that money laundering is harmful for society. I mean, we're talking about money that stems from criminal activities, and it erodes the tax base and so on. And banks have a legal responsibility to try to combat money laundering. But the problem is that we cannot monitor all customers to the same extent, because money laundering is a complicated problem and you need actual people going through cases, which means that we can't do that to the same extent for all of our customers. And so we need a way of prioritizing where to use our resources, and that's where statistics comes into the picture. So we'll start out with the unsupervised learning approach. So basically the thinking here is that one way of thinking about money laundering is as a form of anomaly detection. And a very simplified way of reasoning about this is that most of our customers are not trying to launder money. So if you behave like most of our customers, then you're probably not trying to launder money either. I mean, obviously that's way too simple to think about it, but it is sort of conceptually, we can think of it that way. And so to kind of give you an idea of how this works in practice, I've put together an example where we can imagine that this is a set of our customers. Think of them as sort of small to medium-sized businesses, where on the x-axis we have revenue, and on the y-axis we have cash deposits. And looking at this data, we can see that there's sort of a main cluster of companies having, revenues, about the same, some variation and so on. And the same goes for cash deposits. Now, also note that the x-axis here is on a log scale. So sort of going from the main cluster at 10 to is sort of slightly above it here is a significant increase. Now, looking at this data, it sort of seems like, okay, so we have a normal group of customers, but then we also see that, up towards the left corner, there's this group that seems something slightly different seems to be going on there. And the thing with these customers is that they have, their revenue is typically sort of slightly below average maybe, but they deposit a lot of cash. And then sort of from an anti-money laundering perspective, you might ask the question, okay, so they're not super profitable. Where does all of this cash come from? I mean, why do these companies deposit so much cash? It's basically anomaly detection is kind of a structured way of doing what I've done with these circles here. And of course, in this example with only 2 dimensions, anomaly detection can be done really simply. I mean, you can plot the data and basically just by looking at them, you can spot the outliers. Of course, when you go into the multi-dimensional setting, which is, always the case, basically, in the real world, things get a lot more complicated, because doing this, say you have 19 characteristics or whatever, I mean, taking that whole picture into account visually, it's basically impossible. So that's where statistics comes into the picture. So, okay, we need a statistical way of doing what we just did with our eyes. And one way of doing this is what's known as an isolation forest, which consists of multiple isolation trees. And basically what an isolation tree is you take a data set and then at random, you partition the data along the dimensions in the data. And then you see how many times do you have to partition the data in order to isolate an observation. And as an example, I've shown that this outlier in the top left corner, you don't need to partition the data many times in order to isolate that observation, which means that, okay, that seems like an outlier. And, on the other end of the spectrum, you have the observations, within this big cluster of data. You have to slice the data a lot of times before you're able to get anywhere near isolating those points. So that's sort of intuitively, that's what we want to do. And then I said that the method is called an isolation forest. And the reason for that is that if you do this one time, you risk sort of by chance, maybe you isolate some points very quickly, or maybe you don't isolate points that should be isolated quickly. So what we do is we repeat the process a bunch of times, and then we see for each data point, how many times do we have to partition the data on average to isolate that point. And that gives us an idea of how sort of anomalous or rare that data point is. So that's what I've done here. And what we see is that sort of as expected, for the points within the main cluster, it takes a lot of partitions of the data to be able to isolate them. I mean, in excess of 12. And then once we get towards this suspected cluster of outliers, we see that, we're able to isolate those points way quicker. So this is, we're already home free. But, if we prefer to have sort of a different scaling of this, we can basically take the inverse and rescale the isolation depth. And that gives us sort of an anomaly score between 0 and 1, where we see that, the observations in the main cluster get a fairly low anomaly score. And, as we go towards the edges of the plot, we see that, the anomaly score increases, which is basically what we set out to accomplish. So, okay, now we've kind of a continuous scale of how unusual the data points are. So if we now want to classify specifically, what constitutes an outlier, all we have to do is decide on a threshold beyond which we categorize something as an outlier. And so this figure basically shows, as you go further out towards the tail of the distribution of anomaly scores, how that affects, what constitutes an outlier and what doesn't. And we can see that, if you start at the 95th percentile, most of these suspected outliers are classified as outliers. And then sort of as you go towards the 99th percentile and so on, some of them drop out. And we see that this sort of the main suspect, in the top left corner, basically, stays an outlier no matter what you do. Right. Okay. So this is sort of seems promising. We now have a way of isolating, which data points are unusual. But there is a problem here. And the problem is that if we look at these 2 points, for instance, we see that, based on the anomaly score, they are about equally unusual. Now, the problem with this is that if we look at the point furthest to the right, the main reason that that's considered an outlier is that it's, it has very high revenue. It's sort of a very profitable company. But the problem is, they don't really have many cash deposits. They're sort of average when it comes to cash deposits. Now, the other data points, they're sort of average when it comes to revenue. So the reason they're considered an outlier is, okay, so they have average revenue, but they have, a fair amount of cash deposits, which means that, okay, these are unusual in different ways. And clearly, from an anti-money laundering perspective, the point that you'd want to be concerned about is the one with the most cash deposits. And this way of approaching this problem just doesn't give you that. So summing up, the unsupervised learning approach, I mean, there are some advantages. I mean, it removes the need for observations of money laundering, and we'll get back to that. That is actually quite a big advantage, and it's possibly useful for idea generation because there is something odd about these data points. They are unusual, so maybe looking at them can provide us with valuable information about sort of what's going on and so on. This is actually an idea that we got from a meeting with VIPs a while back that they said that they were doing, and sounded like a cool idea. So we decided to try it ourselves. But of course, there are some disadvantages, and the main one is that this is answering a slightly different question than the one we really want to answer, because something being an unusual data point does not mean that it's money laundering. Which brings us to the next approach, which is supervised learning. When we look at our data, we have historical records of reported money laundering, and based on that, we can build a prediction model to try to determine, what are the characteristics of the customers who have been reported for money laundering in the past, and then use that to try to predict, okay, which customers that we currently have look like the ones we reported in the past. We did this using XGBoost, which is an algorithm that I'm sure many of you are familiar with, and seems to work well for this type of problem. Quickly about the features, we have typical sort of somewhat fixed characteristics. How old are you if you're an individual? If you're a company, what industry are you operating in? And then sort of, I guess, the main type of features here is transaction data. Typically, how many transactions and amounts do you have in different types of transactions? So, do you put a lot of money into cryptocurrencies? Do you deposit a lot of cash? And so on. We've also got, the number of senders and receivers and details about those as well, because networks play a big role in anti-money laundering. So that's important to take into account. And so basically what I've thought is I didn't want to sort of show you the standard variable importance plots and so on, because this is, it would basically look like something you could see on Kaggle or whatever. So instead, I want to talk about sort of what are the specific challenges that we've been faced with for this problem. And the challenges begin with the outcome, where money laundering is both relatively uncommon, and it's something that, because it's criminal, customers who are trying to launder money, they're also trying to hide that they're doing it, which means that we can't perfectly observe the outcome that we're working with. And this leads to a number of consequences. And the first one is that it leads to unbalanced data, very unbalanced data. The problem with that is that you risk having a model that sort of on aggregate seems to be doing fairly well, because, for the people who don't do money laundering, it predicts that they don't do money laundering. And, for most customers, that works well. But the problem is maybe you're unable to detect any money laundering at all. So then, your model is actually useless. One way of mitigating this is by down or up sampling. So we did that. Basically what you do is you throw away some of your non-money laundering observations to sort of balance out the playing field a bit more. But it also means that it's really important to consider, which metrics do you focus on when tuning and evaluating the model. So, metrics such as, the area under the ROC curve is going to work way better here than something like accuracy, where basically, if you predict that there's no money laundering going on, accuracy-wise, you'll be doing fairly well, because most people don't do money laundering. Problem is, in fact, it's a useless model. Right. Some more challenges. Not all money laundering threats or schemas are going to be present in the training data, simply because money laundering is quite uncommon, and so there aren't that many cases of it that we have observed. One example is sort of known high-risk individuals or countries. There are people where you have good reason to suspect that they might be involved in money laundering, but if they've never been a customer at our bank before, we have no way of detecting that sort of empirically, and so a machine learning algorithm is never going to be able to handle such cases fully. And so that's why we also have a set of rules to catch the things that, intuitively make sense that, we need to keep an eye out for this. But we also know that, empirically, the algorithm is not going to be able to catch it. And the last challenge relating to the outcome is that there is actually an interaction between the model and the training data, which comes from the fact that when you use the model to prioritize which customers do you monitor more closely, you have a risk that the model has some characteristics that it finds really suspicious. So you start looking at customers who look like that, and maybe you catch some money laundering there. But the problem is, and then those go into the training data. The problem is, if you keep doing that, then you might end up with a model that's super good at catching that specific type of money laundering, but it might be completely oblivious to anything else. Right. So, because of this, it's sort of tempting that when you're doing this prioritization, you want to, also assign a bunch of customers basically at random for full scrutiny, because that would give you sort of a control group. Problem with that is, it takes a lot of time, so it's expensive, but there is a trade-off there that you really need to think carefully about. Right. So then the features. I'm not planning on going sort of super into the specifics here, but the challenge is that transaction data are complicated. You have bunch of different types of, senders, receivers, types of transactions, and so on, which would be a lot of work to figure out. So I was sort of lucky when working on this that we already have a mapping of transactions that we use for, the app and the netbank, because we want to give our customers information on, what are you spending your money on, and so on. And, another use case for that is this. And another challenge is that, we only observe part of the picture. We can ask someone, where did this money come from, and so on, but going sort of many links back in that chain is going to be really difficult. Right. Summing up, where are we at with money laundering at Sparebanken Vest? So we have a prediction model. Seems to be working fairly well, but we need the rules also to complement it, because not all things will be caught by the algorithm. And we've also got an unsupervised model for idea generation, just to sort of look at outliers. Maybe there's something interesting there. Where do we go from here? Money laundering is something that's constantly evolving, so we need to work on, tuning both the model and the rules to make sure we don't fall behind. And we also have to improve on explainability. And the reason for that is that, in the end, all of these predictions, they go out to actual people who have to go through vast amounts of information with transaction logs and so on, which takes a lot of time. So we'll improve both, accuracy and time use if we're able to give those people, some idea of what to look for, and not just say, there's something about this customers, go look. So thanks for listening. If you thought that was interesting or you want to discuss something else, I'm always happy to chat about these things. So feel free to get in touch.
Yeah, my name is Christer Hadland. I come from the salmon industry, from Grieg Seafood. And today I'm going to talk a little bit about how we use AI and data science for risk assessment. And we have a digital team in Grieg Seafood that does this. And we're 5 people at the moment. So first I'm going to talk a little bit. There's probably not everybody of you know a lot about the salmon industry. So I'm going to talk a little bit about how the salmon industry is and some key numbers, and then what is salmon farming, and then how we work as a digital team in Grieg. And I'm going to show the results of a specific project that we worked on, which is winter source in Finnmark. And then I'm going to show an analytical pipeline of that and demo a risk tool for that. Then I'm going to talk a little bit about successes and challenges. So Grieg Seafood was founded by the Grieg family, Per Grieg, in the 90s. And we have operations. So we have cages, salmon cages in another in Norway, British Columbia, Newfoundland, and we used to have in Shetland in the UK, but we have sold that operation. So these are some members of the Grieg family. And this is how salmon farming was done in the old days. Then you went out to the cage and with the boat, and you fed the fish. So a quite manual process. Today, when feeding the salmon, people are in Rogaland, one of our operation centers. They can sit in this center and feed different cages at sea. So looking at camera, they can monitor the appetite of the fish and look for signals on when to feed and when to stop the feeding. This is how a typical freshwater facility looks like. So typically we rear the fish from when it's an egg from the hatchery, and then we put them into freshwater in a freshwater facility, and then we feed them there. And in this freshwater facility, there's a bunch of sensors to monitor the water quality, so that we have good fish welfare and we have good growth on the fish. And this is how a typical cage looks like today. In average in Norway, there's about 200,000 fish in one of these cages. And at the moment, I think we have about 429 million salmon along the Norwegian coast in the whole of Norway. And if you convert that to biomass, it's about 100,000 tons of biomass. So we actually have more salmon in our coastline than human biomass. So about 3 times more than the human biomass in Norway. So that's an interesting statistic. These are some of we have some closed cages at sea too, that we are experimenting with. So when we have reared the fish in freshwater, we put them into these closed cages, and so that they will adapt faster to seawater. So this is from two of our closed cages we have in Rogaland. So why is salmon farming such a huge business? One part of it is that it has a very good or very low feed conversion ratio. So this means that, for example, if you give between 1.2 or 1.5 kilos of feed to a salmon, you will get approximately 1 kilo of biomass in return. If we compare this to, for example, beef or cattle, you have to give it approximately 6 to 10 kilos of feed to get 1 kilo of biomass. And also you have a quite large edible yield compared to other animals. So this is the distribution of total production of salmon, Atlantic salmon, so farmed Atlantic salmon. Norway constitutes about 60% of the total market of Atlantic salmon production. And these are our production areas that we have. We have, as I told you, in British Columbia and in Newfoundland and in Rogaland and in Finnmark, north of Norway. So what is salmon farming really? Well, it's about mimicking and manipulating natural processes by balancing good fish welfare. And what do we mean by that? That we want the fish to have good welfare, is low mortality, and we do a lot of sampling of the fish to see if it has good health indicators on the skin and other factors on the gills, for example. And we, of course, want to have a high biological and high quality economical output. Yeah, and a little bit about how we work in Grieg. So out on you see on the left corner here, we have a lot of cages that we have the fish in, and there's a bunch of sensors in these cages, for example, for temperature, salinity, oxygen, and current and visibility. And we collect these parameters, and based on that, we can see if the if there's any critical levels, for example, on oxygen, so that the fish will have good welfare, or if, for example, the temperature drop, then we know that it can be critical for the fish or certain bacteria to emerge in the seawater. So we monitor these. This is high frequency data. And then, also the feeders, for example, the ones that sit on an operation center and feed the fish in the cages, they look at cameras that are in these cages and can see how the fish is responding to the feed. And they can also look at welfare indicators. Yeah. And then we have like a cloud where we collect all our data. We also use a lot of external data, specifically weather data, because it can explain a lot of the phenomena we have in the salmon industry. We also have started some collaboration with companies to try to estimate the biomass in the cages with the visual technology. And this is typically how we work. We have a lot of data sources that we pick from our digital platform, so from the sensors in the cages. We also use a lot of research papers to come up with hypotheses on what we should look for in the data. We also pick a lot of environmental data from public sources. And then we try to build a data set by meshing all this data. And we spend a lot of time cleaning and meshing this data. In the analytical pipeline is typically maybe 80 to 90% of the work. And then we do feature engineering, and for whatever problem we want to solve, we try to create models predicting future events, or try to explain things that have happened in the past. And we specifically use R and Python for these kind of things. So the project I'm going to show you today is winter source. That's a big problem in Finnmark. It's due to a bacteria called Moritella viscosa, which typically comes when it's very cold in the water. So in Finnmark, typically in winter, you have down to 2 degrees Celsius in Porsangerfjorden, which is quite cold, and then this bacteria emerges. There's not so much research on why this bacteria emerges. There are some hypotheses, so we wanted to use our production data to see if we could find some clues in our own production data and see if we can make some kind of risk model to model when not to put the fish in sea, or when it's critical for the fish to get this bacteria. And of course, winter source is not good for the fish health. This is typically, if you see on the picture there, there's the wound on the fish. This is how it looks when the Moritella is attached to the skin. So it's the skin quality becomes bad. Also, it causes a downgrading of the fish. So the price of the salmon is also lower usually when you have things like this. And if you do a Google search on it, you will find that there's a lot of salmon farmers that has this problem, and not so many solutions at the moment. So in this specific case, we used 351 harvested cages from 2013 to 2021 in Finnmark. And the way we measure that winter source is a problem is that when you harvest the fish, there's a quality grading of the fish in some quality categories, and the proportion of production A fish, that means fish that has winter source. So in average, 6% of the fish that we harvest in Finnmark is 6%. But it can range from some cages that have had up to 70% of production A, so meaning 70% of the fish has indications of winter ulcer, but also down to almost 1-2%. In this project, we want to explain the variance in this variable here. And also we used about 10 data sources for this project, ranging from weather sensors and internal sensors, so the temperature and salinity and oxygen sensors in the cages. We also used density measures. So there has been some, in the research, there was some hypothesis that density could be an explanatory variable to winter ulcer. We also took data from something called Barents Watch, which is a public source, where you can monitor other salmon producers and see how much lice prevalence they have and how much they produce, etc. Also, we vaccinate our fish. So we have looked into the vaccine history of the fish in this project to see if there are some vaccines that are better than others, because allegedly the vaccines should work against Moritella viscosa. And we looked at a lot of manual inputs as well from the fish farmers, for example, the cage type, and they put some coat layers on the cages that we have registered and so forth. And then we came down to about 400 variables. Of course, some of these variables are derived from the same variable, but we split them up into time-lapse variables. And then we ended up with, this is a little bit hard to see, I can see, but we ended up with 3 models. So one model is that we tried to model the production A and find the drivers of that. But it doesn't help if you have a low production A, but high mortality in the cage. So we had to try to figure out what drives the mortality too. So we want this parameter also to be low, of course, low mortality and low production A. And also we have a weight model. So based on when you put the fish to sea and how long you have it in sea, the model will try to predict the end weight of the fish. So, and we have made a tool that kind of orchestrates like predictions based on input from the user on when you put the fish to sea and when you plan to harvest, and you get a prediction. And the main drivers that we found in the production A model, I will show you in the tool afterwards, but temperature was the main driver. So the colder temperature cycle the fish experience in sea, specifically under 6.2 degrees in the whole cycle. So they're usually at sea between 500 and 600 days in Finnmark. The higher was the prevalence of winter ulcer. So we specifically found that, and then we identified some threshold and implemented this into this model, so that our planners that put the fish to sea can, for example, if they have a planned output in November in North Cape, they can get a prediction on what is the estimated production A and mortality and weight. And in our model, there's a 3% CV error rate approximately. So we had high explanatory value of our model. So I'm going to show a little bit from this tool. It might be a little bit hard to see. So this is a prototype. So it's a simple Shiny app where the user can come with input, and then you get prediction values back. So, for example, if it's a little bit hard to see, I'll try to boost it up a little bit. Resolution is not so good. It's good on Zoom. So here, the user, the planner that puts the fish to sea from our freshwater facility, he can select the temperature curve. So we have temperature curve of each of our localities where we produce salmon. Explain what we have made. Yeah, here we go. Thanks. So the GLM net is easier to explain. It's not so much a black box. So here you get a prediction of 23 and 20% production A if I put out efficiency in August and harvest 500 days later approximately. So how can I get to a lower? How can we get to a lower production A value? So then the planner can click on this include model features. So this is I guess you guys know the Lime package. So this is a framework in Python that in R as well, where you can look at the model features that contributes to a specific prediction. So if I scroll down to the prediction, you can see the components. It's a little bit hard to see here. It's easier in Zoom, so you can maybe look at the recording afterwards. But basically here you can see the features that are driving up the prediction. So one of the features here is broodstock. So that's the genetic strain of the fish we put in at sea. And we have seen that some broodstocks are performing better than other fish in cold conditions. So this means that this specific genetic strain is giving a higher production A prediction. So it's for the planner, so we can see what is driving up the prediction value. So then I can go back to the prediction tool because it gave me some indication that this genetic strain is driving up the prediction. So I can change to another broodstock, and then you see that the production A value is going down. And then I can work myself further down on the prediction by monitoring the features that are driving up the model. So here it says that if the degrees, the average temperature in the whole seawater cycle is under 6.18 degrees Celsius, then that is driving up the prediction value about 3% for this specific prediction. So then I can try to put the fish out at sea, maybe in July instead of August, because in July it's warmer in the ocean. So then it will accumulate a higher average if I try to set it earlier in sea. And then you saw the prediction went down. So then the one model gave 16% and the other model gave 10% prediction on production A. So we made this tool, a simple prototype that where the user, there's a lot of capabilities here where you can simulate different outputs and see the predicted prod A on the same locations or other locations as well. And this is the economics in this. So we had an existing production plan for Finnmark and when to put the fish at sea, and we ran through the existing production model we had in 2021, and then we run it through the scoring models, and we got an estimation of 9% production A, 14% mortality, and with the given sizes that they wanted to put in sea of the fish. And then we tried to make an optimized plan by doing a lot of iteration towards the model to find if there's any optimums on the production plan. So there we weren't allowed to, we had to have the same start date as the original plan, but we could change the size of the fish and when to harvest it. And then we recalculated and came up with an alternative production plan based on the models that would give us the same biomass, but 2% prod A, 9% mortality. But if you see on the right corner, the average of the fish is a lot bigger. So it's bigger smolt, which means a shorter time in sea usually, and then it's easier to get to accumulate the necessary number of temperature degrees in order to lower the risk for Moritella. So, and this equates approximately to, when we've calculated, to 90 million NOK. And also, if you reduce the biomass or reduce the mortality by 5%, this yields approximately 3,219 added tons in biomass. So you can, but by using these kind of tools, it can have a high impact if we were able to implement this production plan. They have done it on some of the areas, especially in the North Cape. They would try to change the output to sea based on our input, but not on all the other ones. So successes and challenges. It's hard to change a production cycle overnight in the salmon industry because everything is dependent on each other. And from when the salmon is an egg, you can manipulate the temperature a little bit to slow down the growth, but there's not much else you can do. And then if new production procedures are coming into the seawater production, then of course the models won't capture that. So it's you have to be a little bit careful if they introduce new production methods and if you're still using your model. And for example, if it's a new genetic strain that comes in our fish, then we can't account for that. Yeah, and some of our successes was that we understand the risk better. So then we can use this tool to, for example, when we should put the fish to sea to get lower production A and lower mortality. And we got to test a lot of hypotheses that a lot of the sea farmers had, and we could narrow it down to some important drivers. That's it. Thank you.
My name is Steinar Søreide, and I'm coming from the company Mjol, and I'm going to talk about how we are using different AI technologies to make media production easier and more fun, maybe. Our company is part of the Fund Group, which is owned by Riber & Son here, and we have a group of different companies, but we are a pure software company, and we are building a product called Mimir. Mimir is a tool for journalists and people that work with media. It's basically a production platform where we are using AI to enhance media. A typical challenge when working with media, especially if you have a big archive, is that logging or having information about the content, metadata, is expensive. So many media production companies and broadcasters, they have large video archives that they basically don't know what's in there. And it's possible to use AI to index the content automatically. And the quality of the different AI services that I will be talking about has increased a lot the last 3-4 years. So this product, the company started actually 4 years ago, about 3.5 years ago, where we saw there was a big need in the market for enabling AI technologies for media workflows. Also, there was a big desire and need to get production moved to the cloud. So those two were the pillars that we built the product upon in the beginning, basically focusing on building a platform that runs in a cloud. It's a software as a service. So the product itself looks like this. I'll get back to the customers. The product itself lives in the cloud. Our customers can sign up for an account, and a typical customer would be a media production company or someone who works in media. Typically large customers that have many journalists and video editors would have a shared account so that all the content that they own can be indexed by our system. and then we plug in to the different the production tools that the users are using every day. So the platform itself, Mimir, is available through a web browser. So some of the users would be using just a laptop to connect to the system, and they would there be able to search and find the content that they are looking for. And then other types of users would have a little bit of infrastructure on premise, like a shared storage, so that they can all work. For instance, if they are editing video, they will be working towards a common storage to avoid having to download all the files to the machine that you're working on. And then some of the larger installations that we have, they have a full newsroom environment with a lot of on-premise servers, where we can do some optimization, because the AI services that we are using today, they typically live in the cloud. We are not an AI company ourselves. We are using a range of different AI services, where we would send the files over to the service to be analyzed, and then we take the metadata back, and then we use that in our tool, and I'll give you a demonstration of how that looks. But in many cases, moving all the content to the cloud is too expensive. And because of that, we also have software that would run on premise, where we can do transcoding, for instance, of media files to lower resolution formats, and also to standard formats that are accepted by the different AI services. For instance, in the broadcast environment, there are many specific broadcast formats that the different AI services would not like. So we have been in production now for about 3 years, and we do have today almost 40 customers, ranging from small production companies to, well, TV2 is testing our system a little bit. It's a small customer. And then we have large broadcasters. For instance, Axel Springer, they launched a TV channel based on our platform, where we do the whole media production asset management. And that's more of the core day-to-day work that the tool needs to do, taking care of getting files into the system, running the AI analysis, making it easy for the users to access it, and also publishing content or transferring files. So there's a lot of workflows that are sitting on top of the core system that has more to do with logistics than the AI services that I will be talking about today. So I think we're going to jump over to the tool itself, because that is more fun. So this is how it looks. This is when I have logged on to Mimir in a web browser, and I can search for content. So I have access to all my folders and all the media that has been uploaded or ingested into my account. And I can search for instance, the word coronavirus. And we try to be like Google for professional video, where you can use an easy interface to search for content. And then we present the search results that are most relevant at the top. And some of the search hits I get are from the titles of the content. And some of them are, for instance, the orange one here, that is a spoken word. And that I can click on. So each line here is a video clip, or it could be pictures and different types of media. And when I get these extra icons on the right side, that means I have a search hit inside some kind of metadata that has a time inside the video. So when I click on it, it will bring up the video.
Coronavirus pandemic.
And we can hear that he's saying the word coronavirus. So this is done using
Coronavirus.
That was a different language. This has been done using a transcription service, so speech to text, basically. And we can combine this with other AI services, for instance, translation. So if I go back to, let's go to the beginning of the pandemic. I'm just marking out the time range here, and that adds it as a filter. So in our tool, we have a filter bar up here. And then I will be able to find some other types of search hits. So we still have, this is probably English. Coronavirus. But this one here looks like a non-English clip. And he's actually speaking Arabic. And if I go into this item, I will see that the original transcript is in Arabic. And I don't read or speak Arabic. But you can see that we have the timing of each word that we have gotten back from the transcription service indexed so that we can visualize it. And then because I search for the word coronavirus, our tool shows me I have one search hit in the translation of this. So basically the English transcript here is done using a different type of AI service that does Arabic to English translation. So our focus is to bring this into the hands of journalists and video editors, those that are creating content, to make it easy to understand and find content that wouldn't be otherwise obvious. I can show you another example. If I go back here to the beginning and then search for, let's do Ukraine and Zelensky. And I'm typing his name now. I'm going to switch off that one. I'm typing it wrong. He doesn't write it like that. And I can search with a fuzzy thing enabled. And that will give me the proper search hits that I'm looking for. So if I go into, for instance, let's choose... I'll try this one. So here we can see the different faces detected in the system. So that's why I ended up having a search hit on this one. If I go to the transcript, we see this is transcribed from Ukrainian. And I see this one here in English. And if I want to, I can easily switch this over to Norwegian. And then we get a Norwegian transcript or translated transcript from the original Ukrainian text. So, of course, the different transcription services and translation services are not accurate. It's not 100% correct, but the quality of these services have increased a lot the last years, so that it's becoming very useful. You can at least get an understanding of what they are talking about by reading the text. We are also using this as a starting point for subtitles. So if I wanted to, I could go into my subtitle view and tune the subtitle. I can make, if you wanted to do, for instance, if this was for linear TV, I would make wider subtitles. And if it's something to be published on the web, I would use fewer words per subtitle so that you would turn it into text that you show on top of the videos and so on. And this can be corrected. We are today not using the training our own models, but it is something that some of the transcription services do support, that you can feed back the corrected transcript to train or improve the models. When it comes to persons, we can see that his name is listed here because his face is detected in the video. And we see the time of where he is visible in the video. So over here, he's not visible, but here he is. And these other people, they are other faces that appear in the video, and they're listed as unknown. And that's also something that we have built into the system, which the standard face detection AI services don't support. You have to pre-train the model before you run the content through it, which is a challenge if you have an archive and you don't even know who is in the content that you are indexing. So we have built a functionality on top of the face detection system that will register a person, an unknown person, as a person object. And then we are able to map all the detections of all the occurrences of that person to the person object, so that even without knowing who it is, there will be a person object in the system that I can click on. And then if there are other occurrences of that person in other videos, even before I know who it is, that will show up here. So I can see that she is actually in 2 different videos detected, and I can go to those search results as well. So as a tool for people that are looking for content, there's a few other AI services that are relevant. I'll show you, for instance, if I'm looking for, I can show you the advanced search menu over here. If I'm looking for content with, let's say, a sunset, I can also use object detection. So this is content that has been indexed using, again, a standard model with labels. And this can be combined with other types of technical metadata that we do get access to. So if I want to have videos with snow, and then I can go to my map view and I can zoom in to Norway, and I can say, I want to have something from, let's say, 2019. So I click on 2019, and then I basically have three filters. I have the snow filter, I have the 2019 as the creation date range, and I have the current map view. And I could also, let's go in this region here. So now I see I have this clip here with snow in it, and it's in the right place and at the right time and so on. So it's when you're using this tool on an everyday, then you also learn how to use our quick syntax for searching. So if I'm looking for person Trump says fake, I'm using this person : and says syntax. And then I find videos where his face is detected.
Fake balls were designed.
And he's talking about fake. And I can also find other videos. So for instance, this one here, his face is in the video. And someone is talking about fake news.
Fake news.
But it's not at the same time. But because we have indexed all the AI-generated metadata, I can also say, I want to show only content where these things happen at the same time. So now I only get the search results where he is in the video at the same time as
fake news.
The word fake is being said. And I can add one more here. I can say, I want to have label flag. And then again, I narrow down my search results. So now I see only those items where those three things
fake
that happens at the same time.
Fake news.
So that's some of the core functionalities that we are using. There's a couple of other AI services that we are using. We also use natural language processing to do automatic tagging of content, basically taking the transcribed text and then sending it to a text analyzer so that we can get the IPTC tags and back from the system to make it also easier for archivists and so on to categorize the content and for people to search and find it. We are, as I said, not an AI company ourselves, so we are allowing our users to choose themselves. So if I go into the language settings here, if I go to, for instance, the English transcription, I can choose between the different AI providers. I don't know if you can read that, but that's Amazon and Google and Microsoft and so on. So our customers can themselves choose which AI services to enable in the system, and also which ones to run on the content, because it's typically too expensive to run it on all the different material that's in the system. So going back here, this one here. Yeah, so as you can see, we are agnostic to what AI services that are used. And I would say, I mean, AI technology, I heard other people building their own models and training their own models. That is not what we are doing. We are basically tapping into the vast library of services that are out there. And from a software development point of view, there are so many good AI services that you can use by just accessing a standard API. You don't need to be a computer scientist with machine learning expertise to use many of these AI services, at least those that we are using today. So I'm going to skip the technical stuff because I think people are ready for a cup of coffee, aren't you? Yeah, I think I spent my time. So that's it. Thank you very much.
I want to thank you all for joining. And I also want to appeal to you, if you have cases, different companies coming here to present for audience, give us a tip on what kind of cases we can showcase to the audience. That would be very nice. And also remember, people in your organization, not the developers, but everybody else, follow on the ABC courses that we will have in AI. Thank you very much and see you next time.